Okay, Chapter 7. We finally get to look at some bit manipulation. So up till now, we've looked at a little bit of organization, basic instructions, moving, copying, comparing, mathematical instructions. We've looked at branching and looping using the jump instructions. We've looked at developing our own functions in assembly language and learning how to where to put them, how to put them in places. We've also learned a little bit about calling conventions. Now it's time to go back and look at some of the x86 instructions that implement Boolean operations. So most other CPUs also have a set of instructions that will do these, but the Boolean operations are really cool. They can operate on multiple pairs of bits at any time. So we're going to look at those instructions that implement Boolean and or XOR and not. We're also going to look at how to shift or rotate bits, which is going to be handy when we rotate especially. Remember we talked about, wouldn't it be handy if I could get to the high order word of EBX or ECX. Rotate will help us get there and do that. So, although they are primitive, bit manipulation instructions are widely used because they provide the sort of control that is, while it's occasionally available in a high-level language, it's not always available. So, let's look at them. As I mentioned, we have instructions for and, or, XOR, and not, generally used to modify one or more bits of an operand. So what are the ways that we might use these? Well, we use logical operations in several different ways. In particular, we can set or clear particular bits. I can also implement Boolean instructions, so implement bools somehow. I can perform arithmetic operations, so, oh, you're going to love this. So we can do some pretty cool math. I can also manipulate ASCII codes. You've seen this in C++. To upper and to lower are functions that you've used before. These are implemented using these Boolean operations. So, before we go any further, let's look at how they work. Let's look at the rules for how they work. In the case of and, or, and XOR, all of these instructions behave this in a very similar way. So all the flags are affected for all three of these. All three can accept the same type of operands, use the same number of clock cycles, and require the same number of bytes of object codes. The operands can be byte word or double word, and the operands can also use any of the addressing modes. All of them are allowed for and, or, and XOR. Not the case for not, so I'll get back to that in a second, but let's look at each one of these one at a time. So, and, what does and do? And, the thing you need to remember is and clears bits. Anytime you need to clear a bit or one or more bits, use an and to do it. So here's the rule. For every 0 in the mask, clear the corresponding bits in the destination, leave everything else unchanged. So, mask. What is a mask? A mask, usually your source operand, it is a value that's used with a logical instruction to alter bit values in the destination. We'll do a couple of examples here in a minute, and hopefully that'll clear this up. So the mask, usually the source, and it's a value that we're going to use to manipulate the destination. So and clears bits or sets bits. Okay, the rule is for every 1 in the mask, set the corresponding bit in the destination, leave everything else unchanged. And then finally, XOR. XOR flips bits. So, for every 1 in the mask, flip or reverse the corresponding bit in the destination. All other bits remain unchanged. Okay? So that's how they work and what they do. Let's look at not before we do some examples. Not, the rules are a little bit different. No flags are affected at all by a not. The operand size, the destination, can be byte word or double word. However, the addressing mode cannot be an immediate value. Okay? So no immediate values. For the same reason, we've never used an immediate value in a destination in any of the other ones. What does not do? Not flips all bits. Flips all bits in the destination. This should be familiar. This is the same as one's complement. Okay? Alright, so there are the instructions. Now let's look at how we can use these instructions. Well, first thing is, what if I want to set the most significant bit of the value? The word set is our hint. When I want to set bits, I'm going to use OR. And here it says I'm manipulating EAX. So EAX is my destination. The only thing I've got to figure out is, what is my source operand going to be? Well, I want to set the most significant bit of the value in EAX. So I'm only looking at, in OR sets bits. I only want to set 1. So I only need the most significant bit. So if I look at the high order byte of EAX, the only bit I want set in the mask is the most significant bit. Okay, so that's going to translate into a mask of 8000000. Okay? Alright, well, hopefully this is making a little bit more sense. Let's do one where we clear bits. Okay? So I want to use these operations to clear the least significant bit of BX. So clear, when I clear bits, I'm going to use AND. My destination is BX. My word size source needs to affect the least significant bit of BX. So again, here I'm looking at, in this case, the low order byte in particular, and I want to clear the least significant bit. And says for every 0 in the mask, clear the corresponding bits in the destination, all else leave unchanged. So the only bit in the mask that I want to be 0 is the least significant bit. So that's going to translate into a mask of FFFE. Okay? So hopefully making a little bit more sense as we go. Well, let's do one more. What if I want to flip bits? Okay, here I want to flip bits. So the operation is going to be XOR. My destination is EBX. And in this case, oh good, we've got something that's going to make this a little bit more interesting. I want to flip bits 3 and 4, and you say, what are 3 and 4? Well, let's look at that. Since that deals with the low order byte, let's look at a byte and just remembering what the ordering looks like. So in this case, this is bit 0, 1, 2, 3, 4, 5, 6, and 7. XOR says for every 1 in the mask, flip the corresponding bits in the destination. So bits 3 and 4 I want to be 1s. Everything else I want to be 0s. Okay? That means that my mask is going to look like this. However, in this case, we notice that we were just manipulating bits in the least significant byte, so I could also say XOR BL, 0.18 hex. Okay? All right. So, are these the only ways I can use this? And the answer is, of course, no. We can do lots of different things. I can do some math. Now, the math, I'm limited, for the most part, to powers of 2, okay, without a little bit more significant manipulation. But this works really well. So, remember when we were calculating the remainder, there's actually a couple of ways we can do it. I can use my division instructions, and I can say, okay, convert double word to quad word. Let's say I'm going to divide something by 32, so I'm going to move into EBX, the value 32, and then I can do IDiv EBX. Whoops, EBX. Okay, so this is one way to do it. However, we remember, oh my gosh, IDiv is gross. 40 or more clock cycles just to do a division instruction. So, is there another way to do it? Well, since I'm dividing by a power of 2, I can. And in this case, we're calculating the remainder, so I want my answer to be in EDX because that's where IDiv is going to put it. So let's first move our dividend, EAX, into EDX. That way EAX remains unchanged, and then I'll manipulate EDX. If I don't care that they're in the same remainder, I don't have to do this move. But here's what I'm going to do. I'm going to AND EDX using the following mask. Okay? And you say, oh my gosh, I have no clue why you're doing this, what you're doing, what it's going to do. Well, let's walk our way through this. Okay? All right, let's suppose we're dividing 35 by 32. When we do that, I know my quotient is 1, my remainder should be 3. Okay? So let's set this up. Let's set up this instruction in a way that's going to help you do this evaluation. So I am ANDing EDX, and we said EDX is 35. That's going to be 23 hex. Okay, that's my destination. And the mask I'm going to put above it. Okay, so my mask is going to be 1F 0001 1111. I've set this up like an arithmetic problem, but don't let that fool you. It's not an arithmetic problem. We're just setting it up that way, but that's okay. So AND, remember what AND says. AND says for every 0 in the mask, clear the corresponding bits in the destination. Everything else will remain unchanged. So these 5 bits remain unchanged. Everything else gets cleared out. Okay? That leaves me with a remainder of 3, since this is in binary. Okay? So what I've done is I've cleared out everything that is 32 or greater, since we're dividing by 32. I can use the same process for dividing by other powers of 2. Okay? All right, let's look at manipulating some ASCII codes, and then we'll call it, well, this one, we'll do this one in class. So let me show you one more instruction, and then we'll call it a video. All right, x86 instruction set includes an instruction that functions the same as AND. So this does the same thing that AND does without changing the destination. So remember when we did compare? Compare did the same thing as subtraction without changing the destination. Test is my way of testing. If I want to test for something being a 0 or something else, I can do that without changing the destination. Let me show you an example. Okay, so test dx 2000. What is this going to do? This is, well, let's kind of draw it out. I'm going to, in particular, draw out the mask. Okay? And remember, this was bit 0, 4, 8, 12, so this bit is bit 13. Test behaves the same way as an AND, so this is going to clear every bit in DX except for bit 13. So in the end, the instruction checks the state of bit 13, and the result is going to be, it's going to look at the 0 flag to tell whether or not the result, when we clear everything out but 13, if 13 is clear, then the result is 0 and our jump will happen. If it's set, then we won't jump. Okay, so that's how the instruction works. So let's call it a wrap with that, and we'll start back up with some shift operations.